The way we're going to find solutions to the hydrogen molecule ion problem is to use an approximation that we call the linear combination of atomic orbitals molecular orbital approximation. So LCAO stands for linear combination of atomic orbitals. And MO stands for molecular orbitals. So we are going to construct our molecular orbitals, our wave functions for the molecule, in terms of linear combinations of the atomic orbitals for the atoms that make up that molecule. So let's think about how we're going to think about doing that. So we have our nuclei A and B. Those are the hydrogen atom nuclei, and we have one electron. So this electron can be a distance RA from nucleus A, and it can be a distance RB from nucleus B. Remember that we're going to use the Born-Oppenheimer approximation, so this AB distance stays fixed at R. So we could really think of this as either the electron is part of nucleus A, in which case we just have a wave function that is for the hydrogen atom being the A hydrogen atom, or this electron is part of nucleus B, in which case we just have a wave function for a hydrogen atom over here at position B. And so our actual wave function then is some combination of the electron just being on A and the electron just being on B. And so if we write that we have a 1s wave function on A, or the electron is in a 1s wave function on B, so they're both in the ground state, then we could imagine that the wave function for the hydrogen molecule ion would be linear combination of that. So I'm going to call this one A, and then I'm going to call this one just B so that it's easier to write this notation. So this could either be the linear combination where we add the two wave functions, or it could be the linear combination where we subtract the two wave functions. Now remember that the probability of finding the electron at some point, r theta phi, is going to be psi star psi d tau. And so since our wave functions are linear combinations, let's take a look at what that probability would look like for the linear combination where we've added the two wave functions. So we'll call this one P sub plus to remind ourselves that this is the one where we've added the two wave functions. So we need psi star plus psi plus d tau. And so that's going to be equal to A plus B complex conjugate times A plus B times some volume element. And so if we FOIL this, we have A star A plus B star B plus A star B plus B star A d tau. And so we can see that these two probabilities are exactly the probabilities that we would get if we just had the electron on one nucleus. So electron all on either A or B and not really split between the two. And these are combinations of A and B, and so these are called the overlap. So this is where the electron is somewhere in between being with A and B, and it's the overlap of those two atomic orbitals. If we do the same thing and look at the probability for the linear combination where we subtracted the two orbitals, we will find that this is equal to the A star A plus B star B, so same as above, but now our overlaps are negative. And so if we use a symbol S to mean the overlap probability densities, then we can write that the probability of the plus or the minus is going to be equal to the probability of being on A plus the probability of being on nucleus B plus or minus this overlap. So physically, the way to think about this is that I have a 1s probability distribution around A, and I have a 1s probability distribution around B. Now remember that these are waves. And so these waves, when they overlap, can either be in phase or out of phase. And if they're in phase, then their amplitudes add to produce a higher amplitude between the two nuclei. If they're out of phase, then their amplitudes subtract, leaving us with a node or a zero probability, a zero overlap between the two nuclei. So in the case of A minus B, we get an out of phase addition of the waves, interference of the waves, and we end up with a node between the two nuclei. Whereas when we're looking at the positive, the addition of A plus B, then those waves are in phase, and we end up with an extra amplitude, a higher probability of finding the electron between the two nuclei. So our A plus B combination results in constructive interference of the waves, and we end up with a probability distribution that adds between the nuclei. And in our A minus B combination, we end up with destructive, because the waves are out of phase, interference, and that ends up with a zero probability between the nuclei, or a node between the nuclei. So we have the possibility of our A plus B having extra probability between the nuclei, so large overlap, and our A minus B ends up with a zero probability between the two nuclei. So S goes to zero between the two nuclei. So this one is called a bonding orbital because it keeps the electron between the two nuclei, which keeps those two nuclei together, forming that bond. And this one is called an anti-bonding. It takes away from bonding because now the electron is more likely to be associated with A or associated with B and not associated with both of them. And that node means that now these two nuclei are not connected to one another by that electron. So if we think about the energies of those two orbitals that we've just constructed, the psi plus, which is bonding, and the psi minus, which is anti-bonding, the way we would find the energies is to find the expectation value for each of these different wave functions. So we would want to take the integral over all space of psi plus star, Hamiltonian acting on psi plus, integrate over all space. And when we do that, we can think a little bit about what that expectation value might look like. So first of all, we're starting with a 1s hydrogen atom orbital, and it has some energy. And because we have our Hamiltonian has this nuclear repulsion term, and as we know, repulsive energies raise the energy of the system. And so if we look at this 1s plus nuclear repulsion, we're going to have a higher energy. So just the fact that we have that nuclear repulsion in our Hamiltonian raises the energy of this 1s orbital that we're looking at. Now, when we add in the effect of the electron being attracted to two different nuclei, we get two different answers, because in the one case, the electron is attracted to the two nuclei and stays close to the two nuclei between the two nuclei. And so there's greater attraction in the plus, the case where I've added the two orbitals together, we have a stronger attraction. And we know that attractive energies lower the energy of the system. And so when we're looking at our A plus B, it's going to be lower in energy because of attraction of the electron to the two nuclei. And the A minus B is going to go up in energy because it has less attraction. Remember that our wave function had that probability of A plus probability of B plus or minus S. And when we subtract S, we end up with an energy that is higher. And when we add S, we end up with an energy that's lower. And so remember that this is our bonding orbital, and this is our anti-bonding molecular orbital. And if we draw this out just in terms of two 1s orbitals combining with one another, so typically the way we draw this is we have the 1s orbital on nucleus A, the 1s orbital on nucleus B, and notice that the bonding orbital goes down some relative to that, but the anti-bonding orbital goes up more than the bonding orbital goes down. And that's because this nuclear repulsion is pushing both of them up. And so when we think about what this looks like when we combine these, we end up with a bonding orbital that's down here, but an anti-bonding orbital that is more destabilized than the bonding orbital is stabilized. So these energy levels in the middle here are our energy levels for the molecule. These are the molecular orbitals. These are the atomic orbitals. And we've combined the atomic orbitals to form the molecular orbitals. We call this bottom one a sigma orbital and this top one a sigma star. So the star is for the fact that it's anti-bonding, and when we're not anti-bonding, we don't put a star on it. So we have sigma and sigma star.